Right now, there is a water harvesting technology that requires no electricity, no moving parts, and no infrastructure of any kind. It has been field tested across 4 continents and reviewed by the USGS, researchers at the University of California, and the UN Climate Technology Center. In the right conditions, an array of collectors no larger than a parking lot can produce tens of thousands of liters of clean drinking water per day. It costs a fraction of what desalination costs. It runs itself. It has already saved entire communities from collapse. And yet if you drive through the American Southwest, through the Texas Hill Country, through drought-hit rural California, you will almost never see one. So why don't we use it? And in a country where the USGS found that nearly 30 million Americans now live in areas of high water stress, should we start? Let's find out. The problem we are not talking about before we get to the solution, we need to understand the scale of the crisis. Because most Americans think of water scarcity as someone else's problem. It isn't. A 2025 report from the U.S. Geological Survey, the first comprehensive assessment of its kind, found that approximately 27 million Americans live in areas with a high degree of local water stress. A separate analysis published in Nature Communications documented nearly 490,000 U.S. households without complete plumbing, and more than 1,100 community water systems in serious violation of Safe Drinking Water Act standards. In Texas, ongoing drought, aging infrastructure, and international water rights disputes have placed the state in a particularly vulnerable position. In Florida, overexploitation of groundwater, which supplies roughly 90% of the state's drinking water, is creating shortfalls even as the population booms. And in 2022, the failure of the largest water treatment plant in Jackson, Mississippi, left approximately 160,000 residents without safe drinking water for weeks. A U.S. Forest Service assessment found that nearly half of the 204 freshwater basins in the United States may not be able to meet monthly water demand by 2071. That is not a distant projection. It is a planning horizon that falls within the lifespan of infrastructure being built right now. This is not a future problem. It is already here. And the solutions we have relied on for the past century, dams, reservoirs, groundwater pumping, are running out of room to grow. The idea that predates civilization, the technology we are talking about, is fog harvesting. And like most of the best passive systems, it is far older than you might think. In the highlands of Chile, the indigenous communities of the Atacama had observed for generations that certain plants, the terra tree, the coastal cactus, seem to thrive without rain, their leaves and spines pulling moisture directly from the Pacific fog banks that roll inland each morning. In the Canary Islands, farmers arranged fields of volcanic gravel into shallow craters to collect overnight dew, channeling it toward the roots of vines planted at the center. And in parts of coastal Africa, certain beetles had evolved a strategy so elegant that 2,000 years later, it would become the subject of peer-reviewed papers in material science journals. What all of these things had in common was the same basic insight. The air around us holds water, even in places where the sky almost never delivers rain. The challenge was always how to pull it out. By the late 1980s, Canadian atmospheric scientist Robert Schemenauer and his colleagues formalized the first modern fog collection system, a flat panel of woven polypropylene mesh stretched between 2 posts on a ridge, angled to face the prevailing wind. As fog-laden air passes through the mesh, the tiny water droplets too small to fall as rain collide with the fibers, coalesce into larger drops, and drain by gravity into a collection trough below. No pump, no filter, no power source of any kind. And the results were extraordinary. In the village of Chungungo, Chile, a fog collection array supplied up to 15,000 liters of potable water per day to 300 residents, enough to sustain a community in one of the driest places on Earth. A study published in the journal Water Science and Technology confirmed the project's long-term viability, documenting consistent supply even during periods of low rainfall. Chilean researchers went further, estimating that capturing just 4% of the moisture contained in the Atacama's morning fog banks, locally called the Camanchacas, would meet the water needs of every community across the entire desert. In Peru's coastal desert, installations were collecting between 200 and 400 liters per day. In Morocco, Ethiopia, Eritrea, and South Africa, similar systems were quietly producing water in communities that had no other reliable source. The technology worked. It was proven. And almost no one in the United States had heard of it. The numbers that should stop you cold. What makes fog harvesting genuinely remarkable is not any single project. It is the consistency of the data across radically different locations and climates. A comprehensive review published by the IWA, the International Water Association, found that typical fog collection systems yield between 1.6 and 6 liters per square meter per day on average across a full year, with peak season rates reaching as high as 10 liters per square meter per day. A 2025 study published in Frontiers in Environmental Science focused on the Chilean city of Alto Hospicio, one of the driest urban areas on Earth, found that a fog collection system using roughly 17,000 square meters of mesh, about 2.5 soccer fields, could theoretically meet the entire weekly water demand of an urban settlement of 10,000 people during the peak fog season in that region. That theoretical ceiling applies specifically to Alto Hospicio's exceptional coastal conditions. Actual yields elsewhere will vary significantly. To put that in terms that are easier to hold, a system taking up less space than a large parking lot, requiring no power and no ongoing maintenance beyond periodic cleaning, could supply meaningful quantities of drinking water for a mid-sized community at the right site, during the right season. In Morocco, the Aqualonis Cloud Fisher Project, currently the largest fog harvesting network in the world, operates 31 large-format collectors across the Anti-Atlas Mountains, with a combined net area of approximately 674 square meters. According to Aqualonis, the system produces an average of 22 liters per square meter of mesh on each foggy day. That translates to roughly 37,000 liters on a productive fog day, enough to provide approximately 12 liters of clean water daily to each of the 1,300 residents across 16 villages the system serves. Zero electricity, zero fuel, zero moving parts. And the cost? A 2025 feasibility study published in Scientific Reports found that fog-harvested water costs approximately 25 cents per cubic meter to produce. Desalination, by comparison, runs between 60 cents and $1.25 per cubic meter for most modern plants, according to industry data reviewed by multiple academic sources, and significantly more for small or remote installations. Bottled water, the fallback for millions of Americans in water-stressed communities, costs orders of magnitude more than either. Why the technology actually works? The physics behind fog harvesting is straightforward, which is part of what makes it so elegant. Fog is not the same as cloud or rain. Fog droplets are typically between 1 and 40 microns in diameter, too light to fall under gravity on their own, and too small to be intercepted by most surfaces. What the mesh does is create an obstacle in their path. As fog-laden wind pushes air through the mesh fibers, the droplets collide with the fibers by inertial impaction. They are too heavy to follow the air around the fiber, so they hit it instead. They cling. They accumulate. They merge into larger droplets, and once a merged droplet reaches a critical size heavy enough to overcome surface tension, it falls by gravity into the collection gutter below. The mesh geometry is everything. Too dense, and wind resistance increases and air stops flowing through, stalling the system. Too open, and droplets pass through without ever making contact. Research published by MIT and conducted across multiple California field sites found that the standard Rachel mesh, a 35% shade cloth made of woven polyethylene, collected 160% more fog water than competing 3D fabric designs at low wind speeds below 1 meter per second, while those competing designs outperformed it at higher wind speeds above 5 meters per second. The conclusion: there is no single best mesh. The right design depends entirely on local wind conditions. This has driven 3 decades of research into next-generation mesh materials, and the results are striking. In 2001, researchers Parker and Lawrence published a paper in Nature documenting that the Namib desert beetle, a small insect living in one of the driest environments on Earth, survives entirely by collecting fog. Its back is covered in microscopic bumps. The peaks are hydrophilic, attracting water. The valleys between them are hydrophobic, repelling it. Fog droplets condense on the hydrophilic peaks, grow until they are heavy enough to roll OA, then slide along the waxy hydrophobic channels directly into the beetle's mouth. That 2001 paper triggered a wave of biomimetic materials research that is still accelerating today. A 2025 study published in Scientific Reports demonstrated that a folded metal mesh inspired by the likwala tree leaf significantly improved collection efficiency across varying fog densities. A separate study published in Micromachines found that a 3D curved surface inspired by the beetle's bumpy back collected water at more than 16 times the rate of a flat surface under the same laboratory fog conditions. And the Aquilonus cloudfisher, the system currently operating in Morocco, uses a proprietary 3D woven mesh that its developers claim outperforms standard Rachel mesh by 36%. Specifically because of its structural depth, which creates aerodynamic turbulence that forces more droplets into contact with the collection fibers. Research cited by the UN Climate Technology Center confirms that fog water harvested this way typically meets World Health Organization drinking standards without any chemical treatment, because the water has never touched the ground, never passed through soil, and has not been in contact with agricultural runoe or industrial waste. It is, in effect, distilled by the natural water cycle and collected before it has a chance to be contaminated. Where it works and where it doesn't, this is the part where most channels would oversell it. We are not going to do that. Fog harvesting is not a universal solution. It is a highly site-specific one, and that specificity is the primary reason it has not scaled globally. The technology works best where three conditions overlap: consistent fog frequency, reliable wind speed to push that fog through the mesh at a rate that produces meaningful collection, and elevated terrain that intercepts coastal fog banks before they dissipate into the inland air mass. The sweet spots, based on decades of field data compiled in the IWA review, are coastal mountain ridges between roughly 700 and 200 meters above sea level, positioned perpendicular to the prevailing wind direction. According to Cloudfisher's documented field data, even a 30-degree deviation from the optimal wind angle can reduce yields by 25%. In the United States, those conditions exist, but they are unevenly distributed. The USG's Pacific Coastal Fog Project has documented significant and consistent fog frequency along the California coast and the Pacific Northwest, particularly during summer months when marine layer conditions produce reliable fog formation over cold coastal upwelling zones. Researchers at UC Santa Cruz identified Pacifica, California as a productive fog harvesting region, and in early 2025, the North Coast County Water District formally partnered with UCSI to deploy 12 fog collector units across Pacifica, the first program of its kind in the state. NBD Nanotechnologies, working under a USTA National Institute of Food and Agriculture grant, has demonstrated in laboratory conditions that advanced superhydrophobic mesh coatings can dramatically improve fog collection efficiency, showing up to a 5-fold improvement over standard nets in controlled testing. Their research targets the coastal California agricultural sector, where irrigation demand is high and groundwater depletion is accelerating. Field-scale validation of these coatings remains ongoing. But install a fog net in Phoenix, Kansas City, or inland Georgia, and it will produce nothing. The technology does not manufacture fog. It only harvests what is already there. And the communities with the most severe water stress in the American interior, the ones drawing from shrinking aquifers, the ones that ran dry in the summer of 2022, are precisely the communities that cannot use this technology. That is the central tension of fog harvesting in the American context. The fog is on the coasts. The crisis is inland. And between the two, there is currently no bridge. So why aren't we using it where we could? Even in the regions where fog harvesting is physically viable, adoption in the United States has been almost non-existent. There are 3 reasons for that, and none of them are technical. The first is an infrastructure mismatch. American water policy is built around centralized systems, municipal treatment plants, pipelines, regional reservoirs. Fog harvesting is inherently distributed and local. A fog net on a ridge produces water for the people on that ridge, not for a city 40 miles away. That model does not fit the procurement frameworks, the regulatory categories, or the federal funding structures that govern how water infrastructure gets built in this country. Decentralized systems are harder to permit, harder to ensure, and harder to justify in capital budget cycles built around economies of scale. The second is a priority mismatch. Until very recently, the communities with the highest fog potential in the United States coastal California, the Pacific Northwest, were not the communities with the most acute water crises. Municipal supplies were adequate. There was no political pressure to invest in supplemental harvesting systems that looked, to most planners, like an expensive experiment. That calculus is beginning to change as California's water future grows more uncertain and drought conditions extend further into traditionally wet regions. The third is an awareness gap. Fog harvesting has been proven at community scale on 4 continents. It has been validated by the USGS, reviewed by the United Nations, published in peer-reviewed journals, and field-tested for more than 3 decades. But it has received virtually no mainstream coverage in the United States, and it has attracted almost no federal research investment compared to desalination or wastewater recycling technologies that require far more energy and infrastructure but fit more comfortably into existing institutional frameworks. The result is a technology that works, is affordable, and is ready to deploy sitting unused in the one country that has both the research capacity and the coastal geography to put it to work at scale. What you can actually do if you live on the fog-prone coasts of California, Oregon, or Washington, particularly at elevations above 300 meters on west, facing slopes. Fog harvesting is not a future technology. It is available today, and the bill of materials is simpler than you might expect. A DIY fog collector using commercial-grade Rachel mesh, the same material validated across the Atacama studies and documented in MIT's field research, can be built and installed for under $100 per square meter of collection area. A well-sited 10-square-meter panel in a productive coastal zone could realistically yield between 16 and 60 liters per day across the fog season, based on EWA documented collection rates. That is enough to cover irrigation for a garden, water for livestock, and a meaningful daily supplement to household supply. The only maintenance the system requires is occasional cleaning of the mesh surface to prevent clogging from dust, pollen, or salt residue. There are no bearings to replace, no filters to buy, no power bills to pay. The system runs on wind and fog, which in the right location are available every day. For anyone in those regions thinking seriously about OA grid water independence, fog harvesting deserves to be the first system you evaluate, not because it will replace your well or your municipal connection, but because in the right location, it is the only passive water system on Earth that can produce meaningful daily yields with zero ongoing cost. For those outside fog-viable regions, the path forward looks dire. The MIT passive hydrogel harvester covered in our previous video is the most promising near-term option for drier climates, but as of mid-2025, it remains a proof-of-concept prototype, not a commercial product. Atmospheric water generators are available now, but they consume significant electricity and produce modest yields, making them a poor fit for true OA grid use. Fog nets are dire. They are real. They are proven across decades and continents. They are affordable enough to build yourself. And in the places where the fog rolls in each morning, there is no passive water system on Earth that comes close to matching them. The fog is already there. The question is simply whether you are